This is Biomaterials, Lecture 10, Video 1. In this lecture, we will continue our discussion of the thermal properties of materials with a focus on the widely used biomaterials used to solve problems in teeth. The key idea for this lecture is free electrons and lattice vibrations are essential to thermal conduction in solid materials. We will discuss one-dimensional steady-state thermal conduction and the mechanisms of heat transport in metals, ceramics, and polymers will be covered in this lecture. We will also talk about using circuit elements to model heat transfer through materials. That's right. You can use some of the concepts that you learned in Engineering 79 to determine the heat transport in materials. Finally, we will discuss a fascinating phenomenon that occurs in our bodies that is called osseointegration. Let's do a quick review. In the previous lecture, we covered thermal expansion and heat capacity. You should understand that as a solid material absorbs heat, its temperature rises and its dimensions increase. Thermal properties like thermal expansion and heat capacity are influenced by the atomic motion around equilibrium lattice positions. Let's discuss how this motion also affects thermal conductivity. Understanding the thermal properties of materials is important for engineers for so many reasons. Some engineers design and build electronic devices, and when these devices operate, they generate heat and increase in temperature. High temperatures can cause intrinsic semiconduction in semiconductor devices, and thermal stresses can lead to a mechanical failure in these devices. Developing solutions to cool these devices during operation also requires an understanding of the thermal properties of materials and heat transfer. Even the design of something as simple as a beverage container requires knowledge of heat transfer. In this thermal image, you can see the differences in performance of 4 beverage containers. Each container has a hot beverage in it, and the brighter the color, the hotter the outside surface of that container. The one on the far left is a glass cup, the second from the left is a ceramic mug, the third from the left is a container designed for holding coffee, and the barely visible container on the far right is another container that has an even better design when it comes to preventing the conduction of heat. Your hands would certainly feel hot if you held the 2 containers on the left, while the third container from the left would feel slightly warm. The container in the far right would feel like room temperature, and you wouldn't know how hot the beverage inside is until you actually take a sip. Let's discuss thermal conduction. Thermal conduction is the phenomenon by which heat is transferred from high temperature to low temperature regions of a material. If we take a look at this simple shape called a plane wall, it has a thickness and a cross-sectional area A. We measure thickness along the axis labeled X. This figure shows a graph of the temperature profile from the left surface of the plane wall. T sub 1 is the temperature at the left surface of this wall. T sub 2 is the temperature at the right surface of this wall. If the thermal properties of the material are uniform throughout, and there is nothing inside the wall that is generating heat or acting like a heat sink, and we assume that conduction is only happening in one direction, which is the X direction, then a graph of the temperatures along the plane wall in the X direction is linear at steady state. Here you see this linear graph of temperatures along the plane wall in the X direction. The high temperature region is the left side of the wall, and the low temperature region is the right side of the wall. When such a temperature gradient exists, thermal conduction occurs and heat is transported from left to right. The energy per unit area that is being conducted per second through the plane wall is called the heat flux. Fourier's law states that the heat flux, which is given by Q sub x double prime, is equal to the heat transfer rate, which is Q sub x, divided by cross-sectional area A. Fourier's law states that the heat flux can be calculated by minus K times the derivative of temperature with respect to X. Note that heat flux has units of energy transported per area per second, or joules divided by seconds times meters squared, or watts per meter squared. The direction of heat flux is shown in the figures that you see here. dt over dx is the temperature gradient that exists in the material. The negative sign in Fourier's law is because we want the heat flux to be a positive value. The direction of heat flow is from hot region to cold region, which means that the slope of the temperature versus x graph is going to be negative. What is important here is K, which is the thermal conductivity, which is a property of a material. Before we dive into thermal conductivity, let's apply what we've learned about Fourier's law. A crown is a cover or cap your dentist puts over a tooth to replace enamel. The crown restores the tooth to its normal shape, size, and function. Let's assume that the mouth has an average oral temperature of 37 degrees Celsius, and the dentine in a tooth is also at that temperature. Let's also assume that the crown has a thickness of 5 millimeters. If we assume one-dimensional, steady-state heat transfer, what is the heat flux through the crown if the oral temperature is increased to 85 degrees Celsius and the crown is made out of gold, which has a thermal conductivity of 297 watts per meter times Kelvin? To enable us to compare the difference in heat flux between a gold crown and natural enamel, also calculate the heat flux for the same case, except use the thermal conductivity for enamel, which is 0.82 watts per meter times Kelvin. Your options are shown here. Please click on the link below to complete this in-lecture question and receive credit for your work. This is an open book, open note assignment. You may take as much time as you need, but the important things to remember in these in-lecture assignments are that you do not ever hit the back button on the form, and you complete the questions before starting Lecture 10 Video 2. We trust you to follow the honor code. We will go over the solutions to this problem in Lecture 10 Video 2, which is also linked below.